In another video, I introduced the idea of a differential equation, which is simply an equation that has a derivative in it. In a differential equation, the derivative can be of any order, but if we consider differential equations of the first order and keep in mind that the first derivative tells us the slope of a function at a point, or more specifically, the slope of a tangent line at a point, then we can get a picture of what a graph looks like by plotting slopes within a coordinate field, or coordinate plane. So when we do that at a lot of points, we get something that we call a slope field, or also known as a direction field. The background of our title screen here, we have a slope field, and that slope field is telling us what functions in a that would solve a particular differential equation might look like. So let's start by talking about what a slope field is, and essentially a slope field is a lot of slope segments, is what they're called, within a coordinate plane, and those slope segments tell you what the function would look like at a particular point, or at a lot of points in the coordinate plane. This one in particular, we can follow the flow of the slope segments and kind of get an idea of what a function might look like. If we just draw a function that somewhat follows those slope segments, we get something that looks like that. Any particular differential equation can have a lot of different solutions. This is because when we take the antiderivative, we get that constant of integration, because when we take the derivative, the constant disappears. And so right here we have a family of solutions to the particular slope field that represents a differential equation here. And these are not all of the solutions. We actually have infinitely many solutions. So we can see here we've got about 10 solutions within a very small region here. So we're going to look at something called an initial condition, which is just a starting point for a function. So given a differential equation and an initial condition, we can get a much better idea of what the function is going to look like. We can start at a given point. We'll say this negative pi 2 is our initial condition, and if we plot that point, we can draw a picture, and this blue curve right here would represent the solution to that differential equation with the given initial condition. Now, we need to talk a little bit about how we might construct a slope field if we were given that task. And to do that, we would simply find the slope at any given point. So if we're given this differential equation here, where the derivative of y with respect to x depends on x and y, and it's simply x plus y, then at a given point, in this case the point negative 2, 1, we can find the slope of a function that would pass through that point that satisfies this differential equation. And we could do that by adding the x and the y coordinate together, since the derivative is equal to x plus y, and the slope is going to be negative 2 plus 1, or negative 1. And so what we'll do is we'll draw a little slope segment there that has a slope of negative 1, and we try to draw that as accurately as we can. And what we'll do then is we'll do this at a lot of different points. In this case, we have 25 points graphed in this coordinate plane, ranging from negative 2 to 2 on both axes. And so, for example, at the origin, the slope is going to be 0 plus 0, and it's 0. At the point 1, 2, the slope is going to be 1 plus 2, so it's going to have a slope of 3. And we can do this over and over again to get an idea of what the slope field is going to look like. Now, just jumping around like this, it's very inefficient, so we might look for patterns. One thing that we'll always want to start with is figure out where the slope is going to equal 0. In this case, since the slope is equal to x plus y, then the slope is going to equal 0 anywhere that x and y are opposite from each other. So, for example, at negative 2, 2, negative 1, 1, 1, negative 1, and so on. So I have indicated that at those 5 points right there where the slope is going to be 0. We can also look for other patterns. We can look for this where the slope is going to be 1. That's going to be anywhere that the x value is 1 greater than the y value, and that'll be along this diagonal here. And so we will draw those in, and looking for similar patterns, we can complete the slope field, and it looks something like this. Now, Here is a more complete slope field. We did it at each integer value. I've included the slope segments at each fourth along both axes. And so this slope field here gives us an idea of what a function might look like if we start at a particular point. When we're constructing a slope field, we can be as accurate and include as many slope segments as we would like. If we're doing it by hand, obviously this many slope segments would be very impractical, and we would want to do something like this using some sort of computer software. If we plot a few different points on here, I've plotted a few, and use those as initial conditions, we can look at what each of the solutions might look like going through those points. And again, doing this by hand, we can get an idea. For example, if we go to, I'll use point I here as an example. Starting at point I right here, we could go up and see that it would look something like that. And then going down, we can see that it's going to look something like this, and it's going to curve up like that. We can get an idea. Drawing it by hand using some sort of computer software is usually much more accurate. And we see that we get a lot of different solutions, and the curves in this family of solutions look somewhat different from each other, depending on where we start. You'll notice that we even have one here that is a straight line. Everything above it is curving up and concave up. Everything below it is curving down, concave down. And you also notice that each one of them approaches this line here. This line turns out to be y equals -1, x plus 1. And they all approach that, and that line is actually the asymptote for all of the others in that family. I want to take just a moment to look at two different families of curves that we've seen so far. This differential equation here and this differential equation here have families of curves that have different properties. You'll notice that each one of the curves in this family look the same, just shifted vertically from each other. So this curve right here is the same as this curve right here, it's just one unit below it. In this family of curves, depending on where we start, we get curves that look differently. The difference between the differential equations here is that this differential equation depends only on x values, and so the slope on any curve is just dependent on the x value, so if we move up along the y-axis, the curve looks the same. This differential equation depended on x and y, so as we move up along the x-axis, we also change the slope by moving along the y-axis. So we get families of curves that look differently depending on if the derivative is a function of x or y or both. I'd like to conclude this video by looking at one more example of how we might construct a slope field. In this case, like I said earlier, we want to look at where the slope is going to be 0, and there are two things that will make the slope 0 for this differential equation. One of them is when y is 0, so anywhere that y is 0, particularly these 5 points in our slope field, the slope is going to be 0. And anywhere that x plus 1 is equal to 0, which is going to be when x is equal to -1. So I started this slope field by plotting everywhere that the slope is going to be 0, and that's when either one of the factors is going to equal 0. And then after that, we'll look for a pattern here, but essentially we're going to calculate the slope at each point. We don't have to show the work for each one of these. It's easy to see here that our x value is -2, so we'll be at, in this case right here, 1, that's our y value, times -1, which is our x value plus 1. We can do that in our head, and we plot a slope of -1, or draw a slope segment with a slope of -1. And doing that at every point, again, each one of these little calculations is not necessary to write down, but we end up getting a good picture of what this function might look like. We could put this together with an initial condition and get a better idea of what a function might look like in this slope field.